I'm going to do chapter 10 before chapter 5 through 9. Because of that, we're going to get information faster than we're supposed to, because chapter 10 in the book assumes that we've gone all the way through hypothesis testing. But we're going to skip through it just because a linear correlation is what most people are looking for first. So we're going to do correlation first, and then I'll kind of explain what you need along the way. So the first thing that we're going to do is draw a scatter plot of the ordered pairs. In a linear correlation, you're comparing x to y. Does this have any effect at all on this other item? After we have our scatter plot drawn, we can find the correlation coefficient that determines how strong, if any, their linear correlation is, how much x affects y or y affects x. And then we'll do some hypothesis testing, with our assumed hypothesis being that there is no correlation. Then we're going to compute the line of best fit, or the regression line, to compute the standard error, and we'll find a predictive interval. So basically, we're going to look at data and see if one is directly correlated to another, see the probability, and test a couple of sets of data. Okay, first, to draw a scatter plot, we're going to label the x and y axis, plot each point on the graph, and then determine if any relationship exists. So here's our first example, the heights of buildings. So consider the following chart. We're going to compare the height of feet in 6 buildings to the number of stories in each building. So we've gone around and we've collected 6 heights and we've counted how many stories there are. Before I get into this, I'm going to show you how to do the scatter plot on your own, because I believe some of the problems do that for you. So I've gone ahead and put your data in Excel, and we're going to highlight the data that we want. Notice that I am highlighting the categories in this case, the height and the stories. I'm going to insert a scatter plot. You can do it through charts, go to R charts, and then all charts, and go to scatter. And we want this first one. Oh, maybe. Okay. So notice that it's already started labeling for us. We need to add some more labels. So I'm going to go to the plus sign over here and add axis titles, and I can go in and edit those. Well, in whatever units, and I can do number of stories here. And you can change your title. Okay, now we also want to, maybe we want to change the color. So you can come over here and you can change the style, you can change the color, you can change everything you want. You can also change anything by double clicking, and you can pop up the right hand pane. And what's going to be really important, and I'll show you it now since we're already looking at it, is that we want to add a trend line, and we'll talk about the regression line later. But anything that you want to add to this, you can, but make sure that it has titles, axes, and that it has your points plotted. You can also add data labels on there. We're not going to right now. But what we want to notice is that we've put all these data points, this X and Y point, on a graph. And then we can compare each to each other by drawing in a line of regression. So that line, or that trend, will tell us approximately what's happening with our data. So looking at this one, we can say that there appears to be a linear relationship between the heights of the buildings and the number of stories. Also notice that my graph looked a little bit different. Notice that they've truncated the axis over here, so it looks different, but it still has the same slope, positive slope that my graph had. Okay, here we have another example. This table shows the relationship between the number of absences of 7 students and their final grade. So notice that the absences and the grade come from the same student. It's one person that we're getting 2 pieces of data from, and then we're using that information to make a comparison about the entire population. So notice that as the absences get larger, our final grade gets smaller. So this kid had 6 absences and he had an 82. This kid had 15 absences with a 43. And if we go the other way, the kid with 2 absences has an 86. So we can tell that this is trending downwards. So we would say that there is a negative linear relationship between the number of absences and a student's final grade. Now that we can look at this information, we can create a scatter plot and we can make a comparison. We can use what's called a correlation coefficient. Correlation coefficient, it's between a -1 and 1. It states how strong your relationship between 2 data points are. If you have a negative relationship, just like we saw in this previous example, it will have a negative correlation coefficient, and it can go all the way to -1. If you have 0, that means you have no correlation. One has absolutely nothing to do with the other. And if you have a +1, like we did in the first example where we had a positive growth, that can go all the way up to +1, and that means there's a positive linear relationship. Again, as x increases, y increases. As y decreases, x decreases for a strong negative. As x increases, y decreases. It's inverse. Okay. So here are some pictures of all the relationships that we can be looking at. For the correlation coefficient to be valid, you first have to check 3 things. The sample must be random. Can't be a convenience sample. The data pairs fall approximately in a straight line. They're measured in an interval or a ratio level. So no category data. The variable should have a bivariate normal distribution. That means that both the x value has to be approximately normally distributed, and so does the y value, so that we can standardize them and then find a correlation coefficient. And we'll get to that equation later, and it looks really gross, but that's what we're doing. So that means that if x is fixed, y should be normally distributed, and if y is fixed, x is normally distributed. Okay, so here we have some examples of the different correlation coefficient. For correlation coefficient, we use the letter R. So in the top row, you'll see that all 3 of these are positively correlated. Notice that from left to right, their data points are getting lined up more and more in a straight line. So a 0.5 linear correlation is, they're positive, but they're not very well grouped together. And then a correlation coefficient of all the way of 1 is, yes, they're a straight line. It's very obvious to see what's happening. And vice versa with a negative. You'll see that this one is spread out, but then as we get closer to -1, we get into a straight line. Okay. So here we have an example. This is the equation in blue over here of the correlation coefficient. This is how you find it by hand. So what it's really happening here, now this equation is gross, but what we're doing is we're standardizing the first variable, x, by finding the z value. And then we're standardizing the second variable, y, by finding the z value. But we have to do that for every x and every y. So then we add them up and we find their averages. And then we multiply the product of their averages. Now we are not going to do this by hand because again, look at this equation. But what we do instead is put it in Excel. So they want us to find this data and we can calculate the correlation. Okay, so I've put the data in Excel so that we can find the correlation coefficient. We're going to find this one part of the equation at a time. So I have the equation on the left and I have my table on the right here. The first thing I want to do is find the product of x and y. So in this column, I'm going to do x times y. Then I'm going to need a total column. So I'm going to put that over here. And I'm going to sum up these values. Okay. Now, so that takes care of this first box. Well, the first place is n, so that's the number of variables, which is 6. So we'll do 6 times this number, the sum that we just found. And then we're going to subtract the sum of x's and the sum of y's. So I need to move this information. I also need to add a sum here because I need the sum of these values. And I need the sum of these values. So I'm just equaling sum in Excel here. Make sure to close your parentheses and hit enter after you've done that work. Okay, so that takes care of the numerator. Now in the denominator, it looks like I need x squared, because I have this number and I have this number. So I need the sum of the x squareds and the sum of the y squared. So almost done here. This is going to be x squared. So that is equal to this number times itself. And then we want to sum them up here. Now don't stress too much about this if you can't remember. I do think there's a problem like this on your homework, so I wanted to walk through it. This is going to be y squared. Okay, so I'm going to do equals y times y. Oops. If you can't get that double click to work, you can just drag it down. Okay. So now to find r, we want to do six times the sum of x and y, so that's here, minus the sum of the x's times the sum of the y values. Notice that I put that in the parentheses. And then I'm going to divide by the denominator, which is the square root. And I just realized I need to put this in parentheses because I'm going to have another square root. Okay. Oh, I don't actually. I'm going to take a second. I'm going to finish typing this in. We're going to run out of time if you have to keep watching me, but I'm going to put all this information in there. Okay, I typed in all of the equation. There it is if you want to see it. And then I'm just going to hit enter afterwards, and my correlation coefficient is 0.927375, so 3 decimal places, 0.927. So I have a very strong correlation coefficient. There's a better way to do that, so I'll talk about that in the next section.